welcome to our next TechBite topic. Today, Kane will be discussing how photonics technologies are being used to detect pollutants and impurities in water. So Kane, what will you be talking to us about today?
Today, Victoria, I will be discussing the world of water monitoring and how photonics can be used in order to increase the accuracy of the measurements taken and build a more accurate picture of what is within their samples. Experts in a variety of application areas often need to be able to analyze their water sources for pollutants, be it directly measuring rivers and oceans, or making sure water is safe to reach our taps. There are a number of optical techniques to measure pollutants at both large and small scales, and Hamamatsu is constantly developing new light sources and detectors which give customers a variety of options for their applications. Typically, the areas of interest fall within the ultraviolet and visible sections of the electromagnetic spectrum, but some applications can also require infrared techniques.
So what techniques are typically used in these kinds of applications?
A lot of applications in this area work in a very similar way. A light source is used to illuminate the water that's being tested, and then a detector is used to measure the light at the other side of the sample. The differentiator between these applications is the interaction between the light and the sample, and as a result, the parameter you are looking to measure at the other side. One widely used technique is absorption measurements. Dissolved organic molecules commonly exhibit strong absorption in the ultraviolet range, and others absorb strongly at specific visible wavelengths. If you have a detector for light at the other side of your sample, it will detect a maximum reading when no molecules are present and the light is going straight through the water. But as more and more molecules are present, then the amount of light detected will be lower and lower. Not all molecules can be measured this way. Some, such as oils and polycyclic aromatic hydrocarbons, fluoresce when they absorb UV light. By measuring this fluorescence, you can then get an idea for the amount of the substance in your water.
But what if the molecule you're looking to measure doesn't interact with light?
That's a very good question. Some molecules don't react to light in their normal dissolved form, but there are two ways of getting around this. The first is to convert the molecule into something you can measure. For example, changing dissolved nitrogen into nitrates, which can then be detected using absorption measurements in the UV region. Other substances can be a little bit more challenging. These are often taken in small samples and then treated chemically in order to produce a colour reaction. Dissolved phosphorus is treated to produce molybdenum blue, and the colour is then measured. This process is known as colorimetry.
So what would I need in order to perform measurements?
Before you make any decisions on what exactly you need optically, it's important to understand your measurement conditions, as this will affect what can and can't work for your application. Firstly, of course, is what molecule or molecules you are looking to measure, as this will affect which of the techniques you will be using, as well as the wavelengths that you will be needing to work with, which by extension will affect the components available to choose from. The components you choose will also affect the precision of your measurements, with the potential of high sensitivity measurements of parts per trillion for some pollutants. In addition to this, it's important to think about the environment and conditions you are measuring in. Are you measuring a large volume of water in situ? Then you will need a powerful light source and a reliable detector capable of taking regular readings. For this, you may be looking at one of our high output xenon flash lamps, and then a phototube that detects the correct wavelength. However, if you are needing to move around and take lots of small samples, then a compact, robust solution is the way to go. For this kind of solution, there is typically a much smaller pathway between the light source and the detector, so something small like an LED selected to a wavelength you need, paired with a solid-state detector such as our photodiodes, image sensors, or even our microspectrometers, for example. These components can allow you to take highly accurate readings of smaller samples and can be moved around easily.
We've discussed a few different methods for measuring water quality. But what if I need to measure multiple molecules at once? Is this possible?
Yes, absolutely, but there are a few things to consider beforehand. Whilst it is technically possible to use one light source and one detector, and measure multiple parameters across multiple wavelengths, it adds a number of complications and isn't cost effective. It is better to isolate your wavelengths, make discrete measurements, and this can be done in different ways. Firstly, you can use multiple light sources, such as LEDs or filtered lamps, which are narrowed to the wavelengths you need for each molecule. Alternatively, you can do the opposite and make discrete detectors, typically by applying a filter to allow only specific wavelengths through. These both make sure that you are reading exactly what you want to be and not another parameter that may not have been considered. However, these don't work for multiple color measurements. In this instance, it is better to direct a broadband light source down multiple channels for each parameter. This can be measured discretely with multiple detectors, or the output from your samples can be recombined and measured with a spectrometer. With technology advancing, and our ability to develop our microspectrometers at a wider range of wavelengths, this kind of measurement will become much more applicable and cost-effective when compared to the other measurement methods in the future, particularly to those looking for something compact or portable.